Hello friends, welcome to my channel. Let's have a look at problem 947. Most stones removed with same row or column. In this video, we're going to share a solution based on countings by finding all the connected components. So first, I'll read through the problem statement to digest the requirements and constraints. And then we do the analysis, and finally we share the code. So here we actually cast this problem into a graph problem, and then we transform the problem to be finding the connected components. So first, let's look at the problem statement. So on a 2D plane, we place n stones at some integer coordinate points. Each coordinate point may have at most one stone. A stone can be removed if it shares either the same row or the same column as another stone that hasn't been removed. So this paragraph actually is very important. So if we regard this problem or interpret this problem as a graph problem, so this paragraph actually tells us when there is a direct edge between two stones. So the problem asks us to that for giving an array stones of length n, so where stones I equals xi, yi represents the location of the ith stone. So return the largest possible number of stones that can be removed. So here are three examples. So example 3 is very special because there is only one stone, so the number of stones we can remove is 0. So you can actually interpret the 5 in example 1 and 3 in example 2 according to the explanation in the examples. So we are going to look at example 2 in some details later. So the constraints for this problem are the following. First, the list length is bounded below by 1, in other words non-empty, and bounded above by 1000. So this 1000 is a small problem because if you compute 1000 square is 10 to the power 6, so it's still doable, right? So the secondly, xi and yi, the coordinates are non-negative. In other words, so all the points are in the first quadrant in the coordinate system. Secondly, so no two stones are at the same coordinate point. So this is for consistency, or we can say it brings us convenience for the counting. So this is the problem statement as a constraint. So now let's look at the method. So here we want to find all the connected components, right? So within one connected components, the number of stones can be removed is the number of nodes in the connected component minus 1, right? So here, this problem actually is straightforward once we make this interpretation or identification. So assume that each connected component contains ni nodes. So we just need to sum those ni minus 1 with ni when ni is greater than 1. So for sure, ni minus 1 equals 0 if ni equals 1. In other words, there's a single stone cluster. So in this case, so in view of this fact, so we can just sum up all the ni minus 1s, right? So here actually in the implementation level, so we could use an index to represent a node, or we can use a coordinate pair depending on our preference. As for finding the connected components, so it's actually a routine problem. So we could use either traversal-based methods, such as breadth first search, depth first search, or we can use disjoint set union. In other words, the union find method. So here, let me give you a walkthrough without specific to a method. So here we have example 2, right? The two connected components are the following, right? So this is C1 is a connected component 1, and C2 is connected component 2, right? So if we do the number of stones we can remove, that is 4 minus 1 plus 1 minus 1. So in total is 3. This is the 3 in example 2. So let me mention this paragraph again. So two nodes or two stones are there is a direct edge between two stones if they share x coordinate or y coordinate. So with that said, I guess implementing a solution is rather straightforward. So here I'm going to implement using UnionFind. So actually we have a special playlist for UnionFind, and we implement or practiced quite a number of problems which can be solved using UnionFind. So here we are going to give a quick implementation without explaining too much about the details. And for interested audience, you can actually check out the corresponding playlist. So for this purpose, first I'm going to get the n, this is the length of the stones. So this is just for convenience. And then let me first do part 1, so UnionFind. So this is actually very routine, right? So first I'm going to do some initialization. So here I choose to implement the UnionFind data structure inside this function. So actually we can do outside this function or outside this class. So it depends on the specific application cases. So here let me do this. Root equals, let's see, I 1 I. So for I in range n. So here I'm using the dictionary roots rex. So which is I 1, right, for I in range n. So you can interpret this rec initialization as that. So originally we have single stone cluster, right? So we want to do the union operations according to the problem logic. In other words, the paragraph 2 in the statement. So first let's implement the find method. So here I'm going to use path compression. Right. So for this, I'm going to introduce a result just for convenience, and then the while loop, so very standard. Result does not equals roots of result. So if this is the case, basically what we want to do is that we want to retrieve above this chain, right? So we set result to be the roots of the result. So finally, we are going to return a result. The reason is that after we exit this while loop, the result will equal to roots result, right? But in between here, let's do compression. So we set the roots of the result to be the roots of result. So we can interpret this roots as an operator. So here we apply this twice, right? So this is the find, and now let's define the union. So the union accepts 2 nodes. So here we do not need to return anything. So let's first find the root I, root j. So this is simple, right? Find I, find j, right? So for this, let me check if root I equals root j. So we do not need to do anything. Otherwise, they are not the same. So in this case, we want to do join, but we want to do join by rec. So let's see, union by rec. So now we check, so if rex root I is no less than rex of root j. So in this case, we are going to set the roots of root j to be root I, right? And then we are going to increment the rec of root I by that of root j. So let's change this one to be add, right? So this is the one case. In other case, so we do the same thing, but we reverse the direction. So in other words, we set the root of root I to be root j, and then we increment the rec of root j by that of root I. So that's it for this union by rec function. So next we want to write the problem logic. So problem logic. So for the problem logic, what we can do is the following. So we can do double for loop due to the problem size. So for I in range m, so we want to represent a node using the indices. Then we want to check for j in range so I plus 1 and the m. So as we consider two-way edges or undirected edges, so we just need to do it from I plus 1 up to n minus 1. So in this case, what we're going to do is if we check if there's a direct edge. So in other words, we want to say stones I 0 equals stones j 0. So this means the two stones share the x coordinate. Or, so let's see, we do this. Let's change this 0 to be 1. So this means that they share the y coordinates. So let me put a parenthesis just to make the logic clear. And then if this is the case, we are going to do union operation. So union ij, right? So this is the problem logic. So now let's look at the return, right? So let's see the return. So we want to count the different clusters or connect components, and we are paying attention to the counts of nodes in each cluster. So let's do this. So D is a dictionary, right? Then for so let's see, for let's see I. So we can do this. Let's see, for I in range n. So this is a node. So what we want to do is we find its root. So this root is find I. So this is just one way to do this, right? And then we're going to do the counting directly, right? So let's see, we'll set d of the root, so equals d get. I'm going to use this function. If root is not inside d yet, so we're going to set its value to be 0. Then we add 1 because we want to add this stone to that cluster. So this way we get cluster. So what we want to return is nothing but sum of v minus 1 for v in d values. So this is our return. So in other words, this is the number of stones we can remove. So before we do anything, let's first do a check. Yeah, it passes the first example. Now let's look at generic case. Yeah, it passes the generic case, all the cases. So here, actually, let me print out the different clusters so that we can have a better understanding. So let me copy this part. So actually we can write this even shorter, but that's not our purpose. So here we want to do this. So if root in dd, so what we're going to do is that dd root, so I'm going to add this I, right? Otherwise, so I'm going to set dd root to be a set, right? To be a set with this one. So then actually I can print out this dd, right? So let's check. So for example 1, so we get this. So this is a single cluster, so which contains 6 stones. So we can remove 5. So now let's look at example 2. So for this, so we have 2 clusters. So here's one cluster represented by 0, and this another one represented by 2. So here we can remove 4 minus 1 plus 1 minus 1, that is 3. So let me comment out this part and do the check again. Yeah, it passes all the cases. So as we mentioned, that actually this problem can be solved using binaries, using not binary, breadth first search or depth first search. So it's actually good to have a try. So with that said, I guess that's about it for this video. Thank you.